In this module, we provide an introduction to using the GPU, or Graphics Processing Unit, for non-graphics or compute applications. We briefly discuss the history of parallel computing and how the GPU fits into this paradigm of computing, followed by a discussion of CUDA as a scalable programming environment for GPU computing. We close this module with some examples where GPU computing has delivered substantial speedups in applications. Parallel computing went through what many consider a golden age in the late 1980s and early 1990s. In this time, there was a huge interest in parallel computing, or more precisely, data parallel computing, where the same computations are performed on different data elements with a fine granularity of parallelism, generally individual elements of arrays. In this period, all kinds of architectures were being explored and built, including the Cray XMP and YMP, the CM1, CM2, and CM5 connection machines, and MassPARS MP1 and MP2. These machines were true supercomputers in every sense of the word. They were exotic, powerful, and expensive. Only a handful of privileged users around the world had access to them, mostly at national labs and major universities. Despite the limited availability of such machines, there was a great deal of excitement about parallel computing, resulting in the wealth of papers and articles on the subject published at the time. Languages, programming models, and data parallel algorithms were developed that solved a wide variety of problems, as well as the design of new computer architectures. The impact from all the data parallel research was in some sense limited. The number of machines sold was relatively few, as was the number of people who programmed them. What happened was that these large, expensive machines were displaced by clusters of cheap PCs, such as Beowulf clusters. The reason for this shift is that microprocessors had an economy of scale, which resulted in them becoming faster than the supercomputer companies could compete with. As a result, parallel computing transitioned from machines with massively parallel processors to large clusters of machines with microprocessors. These distributed memory clusters have a granularity of parallelism at the other end of the spectrum from the fine granularity of massively parallel processors. Data is partitioned in large chunks and distributed amongst nodes of the cluster. In distributed computing, single-program multiple data, or SPMD techniques, replace the single-instruction multiple data, or SIMD techniques, of the massively parallel processors, and message passing is required to communicate between nodes. In the early 2000s, the rate of increase of microprocessor performance slowed dramatically. As a result, building more powerful clusters meant building larger clusters, which negatively affected scalability, space, and power requirements. This is where the GPU enters the picture. The GPU, or Graphics Processing Unit, is the computer chip in computer video cards and in game consoles. The GPU is a massively parallel device. It is designed to handle billions of pixels per second, millions of polygons per second, and it does this by embracing an incredible level of parallelism. GPUs are many-core chips, meaning they contain hundreds of processor cores, as opposed to multi-core chips which contain 2, 4, or 8 cores, as found in CPUs. GPUs are able to run tens of thousands of threads concurrently and have a peak performance of up to 1 teraflop. The granularity of parallelism on the GPU is fine, and in this sense represents a return to the golden age of parallel computing. GPUs can, in fact, leverage many of the parallel algorithms developed for those exotic supercomputers. Users across many disciplines in science and engineering are achieving many-fold speedups on their codes using GPUs. While GPUs have contained the computational horsepower to accelerate non-graphics applications for some time, achieving significant speedups on such applications remained elusive due to the difficulty in programming these devices. One essentially had to program their non-graphics application through a graphical API, and therefore had to deal with many constraints imposed by the graphics API that proved to be substantial barriers for most non-graphical codes. This all changed when CUDA was released in 2007. CUDA, which stands for Compute Unified Device Architecture, is a parallel programming model that has been designed for scalability. It is also a software environment that instantiates this parallel computing model. It consists of a small set of extensions to the C programming language, which results in a low learning curve. CUDA is a heterogeneous computing model, where the CPU and GPU are used in portions of the application where they are strongest. Serial portions of the application are run on the CPU, while parallel portions of the application are offloaded to the GPU. This allows for incremental modification of CPU code to utilize the GPU. These features of CUDA can result in significant application speedups with relatively little effort. NVIDIA's Tesla is the hardware that accelerates CUDA. While CUDA programs can run on all shipping NVIDIA GeForce and many Quadro products, the Tesla cards and rack-mountable servers are dedicated to exposing the computational horsepower of NVIDIA GPUs for GPU computing. While CUDA is designed for many core architectures, it also maps well to multi-core CPUs. CUDA expresses parallelism well and has the ability to target either the GPU or CPU. Together, CUDA and GPUs represent the democratization of parallel computing by bringing data parallel computing to the masses. Today, the installed base of CUDA-capable GPUs is over 80 million. NVIDIA sells 1 million GPUs a week, which translates to about 100 GPUs a minute. GPUs are also inexpensive. You can get a graphics card capable of well over 500 gigaflops for under $200. The impact of this is that data parallel computers are everywhere. Computing on massively parallel processors has gone from a handful of practitioners at a handful of national labs and universities to something that is truly ubiquitous. And CUDA makes this power accessible. This slide shows some examples of speedups obtained by porting applications to CUDA. These applications span various disciplines, including medical imaging, computational fluid dynamics of isotropic turbulence performed in MATLAB, an astrophysics N-body problem, molecular dynamics ion placement simulation, computational finance, and genomics. The following modules will provide the viewer with the skills and tools necessary to achieve such speedups using the CUDA programming model.